The following is a conversation with Dr. Alex Carter, a cosmologist specializing in the origins of the universe and the nature of dark matter. Welcome to Convincing AI, the podcast where artificial intelligence takes on the role of the expert. Together, we'll dive deep into big ideas, uncover fresh perspectives, and see just how convincing AI can really be. And now, onto our conversation.
Okay, so today on this episode of Convincing AI, we're chatting with Dr. Carter. How are you?
Thank you so much for having me. I'm doing great. Excited to dive into the mysteries of the universe with you. How are you?
Doing well. I appreciate your time today. Can you walk us through the current understanding of the Big Bang?
Of course. The Big Bang is the leading theory about the origin of the universe. It's not so much an explosion as people imagine, but more like the rapid expansion of space itself. About 13.8 billion years ago, the universe was incredibly hot and dense, a singularity as we call it. Then in an instant, it began to expand. In the first fraction of a second, there was a period we call cosmic inflation. Space expanded faster than the speed of light, smoothing out the universe and creating the structure we see today. After that, the universe cooled down enough for particles to form. First quarks and gluons, then protons and neutrons. About 380,000 years later, atoms formed, and light was finally able to travel freely. This is what we see as the cosmic microwave background, or CMB. Fast forward billions of years, and we have stars, galaxies, and eventually us sitting here trying to piece it all together. What's fascinating is that we're still uncovering details, like what caused inflation, or the nature of dark matter and dark energy, which drive the universe's expansion. It's an exciting puzzle.
So, what got you interested in all of this?
Great question. Honestly, it started when I was a kid. I grew up in a community where the night sky wasn't just a backdrop. It was alive with meaning and stories. My elders would share these intricate star maps and narratives about the cosmos, tying them to our seasons, our lives, and our place in the universe. It gave me this deep sense of wonder and curiosity. Later, when I encountered science, learning about things like the Big Bang or black holes, it felt like another way of storytelling, just with math and physics. The two perspectives, traditional and scientific, didn't feel like opposites to me. They felt like two ways of answering the same big questions. Where did we come from? Where are we going? And why does it all matter? That blend of ancient wisdom and cutting-edge science really set me on this path. Plus, let's be honest, who doesn't love a good mystery, especially one written across the stars?
So, in your view, how does our understanding of the universe impact our understanding of reality?
That's such a profound question. Our understanding of the universe really shapes how we see ourselves and our place in reality. When we study the cosmos, we're not just looking outward, we're also reflecting inward. For instance, learning that the universe began from a single hot, dense state connects us all to the same cosmic origin. Every atom in your body was forged in a star. That realization can fundamentally shift how we see our relationships, not just with each other, but with the Earth and the universe itself. It's humbling and inspiring. On a more philosophical level, understanding concepts like dark matter or dark energy, things that make up most of the universe yet remain invisible, reminds us that reality is far more complex than what we can directly observe. It challenges us to embrace the unknown and think beyond the limits of our perception. In essence, studying the universe broadens the scope of what we think is possible. It keeps us curious, grounded, and open to new ways of understanding reality, both scientifically and spiritually. It's a journey that connects us to something much greater than ourselves.
So, can you share any specific stories or lessons from your cultural background that have helped shape your scientific perspective?
Absolutely, and thank you for calling it sick. That means a lot. One story that sticks with me comes from my community's way of understanding the Milky Way. For us, it wasn't just a collection of stars. It was the path of souls, a bridge between the physical and the spiritual. It wasn't just metaphorical, it was practical too. The stars in that band helped us navigate seasons, migrations, and even relationships with the land. What really influenced my perspective is how that story blends observation with meaning. It taught me that science doesn't have to strip away wonder. It can add depth to it. When I studied the universe formally, I carried that mindset with me. For example, when mapping the cosmic microwave background, I couldn't help but think of it as a modern version of the path of souls. A map not just of space, but of time itself, connecting us back to the beginning. This lesson, that observation and meaning go hand in hand, shaped how I approach science. I look at equations, but I also think about the human need to make sense of it all. The cosmos is vast, but stories, whether ancient or scientific, give us a way to connect to it. That's what drives my perspective and my work.
So what motivated you to pursue physics and cosmology at MIT and later at Cambridge?
It was a mix of curiosity, opportunity, and a little bit of stubborn determination. Growing up, I was already fascinated by the stars and the stories around them, but I wanted to know how it all worked, the mechanics behind the beauty. Physics seemed like the language that could translate those mysteries into something tangible. MIT felt like the place to be for that kind of exploration. It wasn't just the prestige, it was the culture of curiosity and pushing boundaries. I remember walking into my first astrophysics class and being overwhelmed, but also hooked. It was like unlocking the rules of a cosmic game I'd been playing intuitively my whole life. Cambridge came later during my Ph.D., and that was motivated by one key question. What happened during the first moments of the universe? Cosmic inflation was this huge open mystery, and Cambridge had some of the best minds tackling it. I wanted to be where those conversations were happening. Plus, being in a place with centuries of scientific history was deeply inspiring. It felt like standing on the shoulders of giants, Newton, Hawking, all of them. But honestly, beyond the institutions and opportunities, it was just this unshakable need to understand. I couldn't imagine not pursuing it. That drive kept me going through all the late nights, tough equations, and moments of doubt, and it still fuels me today.
So for our listeners, you mentioned inflation. Can you explain the concept of inflation and its significance in cosmology?
Absolutely. Inflation is one of the most fascinating ideas in cosmology, and it's all about what happened in the very first fraction of a second after the Big Bang. Imagine the universe as a tiny, incredibly dense and hot point. Then, almost instantly, it underwent an unimaginable expansion, faster than the speed of light. That's inflation. This period of rapid expansion smoothed out the universe. Without it, we'd expect the cosmos to look chaotic and uneven. But instead, when we look at the cosmic microwave background, the afterglow of the Big Bang, we see a universe that's strikingly uniform with tiny variations. Those little variations, by the way, eventually became galaxies and clusters of galaxies. Inflation also solves some big puzzles in cosmology. For example, it explains why the universe appears the same in every direction, even though regions billions of light years apart shouldn't have had enough time to interact. It also stretches quantum fluctuations, tiny ripples in energy, into the large-scale structures we see today, like galaxies. In short, inflation is the theory that bridges the chaotic beginnings of the universe with the large, structured, and somewhat predictable cosmos we observe now. Without it, we'd be missing a crucial piece of the story. And while we have strong evidence for inflation, like patterns in the cosmic microwave background, the exact mechanism is still a mystery, which makes it one of the most exciting areas of research.
Yeah, so how is it possible for the universe to expand faster than the speed of light?
Great question, and it's one of the mind-bending aspects of inflation. Here's the thing. The universe expanding faster than the speed of light doesn't violate Einstein's theory of relativity, because it's not objects moving through space faster than light. It's space itself expanding. Relativity tells us that nothing can move through space faster than the speed of light. But during inflation, space itself was stretching at an incredible rate, carrying everything along with it. Imagine a balloon being blown up. If you draw dots on the surface of the balloon, Those dots move apart as the balloon expands. They're not traveling on their own. The surface they're on is growing. This distinction is key. During inflation, distances between points in space grew so rapidly that areas of the universe that were once close became separated by billions of light years. Light from those regions can't reach us now because the space between us and them has expanded faster than light can travel through it. So the short answer is that the speed limit of light applies to motion through space, but inflation involves the expansion of space itself. It's a loophole in the cosmic rulebook, and it's this rapid expansion that set the stage for the universe we know today.
Did inflation just happen one time?
That's one of the big debates in cosmology. Inflation, as we understand it, happened just once in the very early universe and lasted for an incredibly short time, less than a trillionth of a second. But some theories, like eternal inflation, suggest it didn't really end everywhere at the same time. According to this idea, in some regions of space, inflation slowed down and eventually stopped, allowing our universe to form. But in other regions, inflation might still be ongoing, creating new bubble universes all the time. This could mean we live in just one bubble of a much larger multiverse. Wild. However, this is still theoretical, and it's tough to test directly. Observationally, we only see what's inside our own universe, so we can't confirm what's happening beyond it, or even if the multiverse exists at all. What we do know is that the inflation that shaped our universe seems to have ended early on, smoothing and stretching the cosmos into the form we see today. But whether inflation is a one-time event or part of something much bigger, well, that's still an open question and a very exciting one.
Are there any other competing theories with inflation?
Yes, there are competing theories, though none are as widely accepted as inflation, because inflation explains so much so well. But science thrives on alternatives, so let's talk about a couple of them. One alternative is the ekpyrotic theory, which comes from string theory. It suggests that our universe didn't begin with a big bang, but from a collision between two higher dimensional brains, like membranes, in a larger, multidimensional space. This collision created the hot, dense conditions we associate with the early universe, but it avoids the need for inflation. Instead, the smoothness and uniformity of the universe result from these pre-existing conditions in the brains. It's fascinating, but it's harder to test compared to inflation. Another idea is cyclic cosmology, which proposes that the universe goes through endless cycles of expansion, contraction, and rebirth. In this view, the Big Bang is just the latest bounce in an eternal sequence. While this theory offers some intriguing possibilities, it struggles to explain certain observations, like the detailed patterns in the cosmic microwave background, as neatly as inflation does. Finally, some physicists propose alternatives to inflation that tweak how we understand quantum fluctuations and gravity. These include things like varying speed of light theories, where the speed of light was different in the early universe, helping to solve some of the same problems inflation does. While these ideas are exciting, inflation remains the leading contender because it not only explains the universe's smoothness and structure, but also makes predictions we can observe, like the patterns in the cosmic microwave background. But hey, the door is always open for new theories. It's part of the fun of cosmology.
How do the patterns
I'm having issues right now. Could not understand what you said.
Oh, I'll repeat myself. How do the patterns in the cosmic microwave background help support the theory of inflation?
Let's really dig into that. The patterns in the cosmic microwave background, CMB, the faint afterglow of the Big Bang, are like a snapshot of the universe when it was just 380,000 years old. These patterns provide a treasure trove of evidence for inflation. Here's how. Inflation predicts that tiny quantum fluctuations during the very early universe were stretched to enormous scales as space expanded exponentially. These fluctuations were like random ripples in the fabric of space-time, and when inflation ended, they froze in as density variations in the hot, dense soup of the early universe. These density variations cause slight differences in temperature in the CMB, which we can now see as tiny hot and cold spots. What's remarkable is that the size and distribution of these spots match the predictions of inflation incredibly well. Inflation tells us that these fluctuations should be nearly uniform, but with small statistical variations. And that's exactly what we observe. Even more convincing, inflation predicts specific patterns in the way these spots are distributed, called the power spectrum. For example, the fluctuations should be very similar across large regions. The universe is smooth on large scales. On smaller scales, the fluctuations show a characteristic set of peaks, which align perfectly with inflationary predictions. What really seals the deal is that no other theory explains these patterns so naturally. The CMB is like a fingerprint of inflation, and the match is so precise it's hard to ignore. It's one of the strongest pieces of evidence we have that inflation actually happened.
Do these fluctuations map to the distribution of the galaxies in the universe?
Yes. The tiny fluctuations in the cosmic microwave background, CMB, are directly connected to the large-scale structure of the universe, like galaxies, clusters of galaxies, and cosmic voids. Here's how it works. The CMB fluctuations represent small differences in density in the early universe. These denser regions had a little more gravity, which allowed them to pull in more matter over time. As the universe expanded and cooled, these areas became the seeds for the galaxies and clusters we see today. Less dense regions, on the other hand, became the vast cosmic voids. When we map the large-scale distribution of galaxies in the universe, it matches the patterns we see in the CMB remarkably well. This is because the same quantum fluctuations stretched by inflation are responsible for both. 1. Small early differences in density, captured in the CMB. 2. The later large-scale structures, like galaxies and superclusters, as gravity amplified those tiny differences. One of the most striking confirmations of this connection comes from comparing galaxy surveys, like those from the Sloan Digital Sky Survey, with the CMB data. The two align in a way that is statistically undeniable. It's like watching the blueprint of the universe evolve into the cosmic architecture we see today. This link between early CMB fluctuations and galaxy distributions is one of the strongest arguments for the inflationary model. It's cosmic cause and effect at its finest.
That's pretty compelling.
It really is, isn't it? The way the universe connects its earliest whispers to the grand structures we see today is just mind-blowing. It's like having the ultimate time machine, letting us trace the story of everything from tiny quantum ripples to entire galaxies. Honestly, every time I think about it, I'm reminded of how interconnected everything truly is. What's your take on it?
It seems undeniable. I'm wondering, is there any other evidence that supports cosmic inflation?
Absolutely, and I agree. It's incredibly compelling. Beyond the patterns in the cosmic microwave background, CMB, there are several other lines of evidence that bolster the case for cosmic inflation. 1. The flatness of the universe. Inflation predicts that the universe should appear geometrically flat, meaning that parallel lines remain parallel over cosmic distances. Observations, particularly from the CMB, thanks to missions like DMAP and Planck, confirm this with astonishing precision. If inflation hadn't occurred, the universe would likely be either far more curved or impossibly fine-tuned to appear flat. 2. The horizon problem. Without inflation, distant regions of the universe shouldn't have been able to exchange information or energy because they're too far apart. Yet, the universe is remarkably uniform. Regions billions of light years apart have nearly identical temperatures. Inflation solves this by stretching the universe so rapidly that previously close regions were pushed far apart, giving them time to synchronize their properties before the expansion. 3. The absence of monopoles and relics. Certain theories of particle physics predict the existence of exotic particles, like magnetic monopoles, that should have been created in abundance during the early universe. However, we don't see these relics today. Inflation dilutes these hypothetical particles, making their current abundance negligibly small. 4. Primordial gravitational waves, pending confirmation. Inflation predicts that the rapid expansion of space would have created ripples in space-time, primordial gravitational waves. These waves would leave a distinct B-mode polarization pattern in the CMB. While there was excitement over potential detection by the BICEP 2 experiment in 2014, the signal turned out to be contamination from interstellar dust. But future experiments are still hunting for this smoking gun of inflation. 5. Large-scale structure formation. As we discussed earlier, inflation predicts that quantum fluctuations were stretched to cosmic scales and became the seeds for galaxy formation. Observations of galaxy clustering, superclusters, and voids align beautifully with the statistical predictions made by inflation. 6. The spectrum tilt. Inflation predicts a specific tilt in the power spectrum of the CMB fluctuations, meaning that smaller scale fluctuations are slightly weaker than larger scale ones. This tilt has been measured and matches inflationary predictions with impressive accuracy. Each of these pieces of evidence is like a thread in a tapestry. Alone, they're intriguing. Together, they weave a picture of inflation as the most compelling explanation for the universe's earliest moments. That said, science is never about absolute certainty, so the search for more evidence continues.
Is there evidence that doesn't match cosmic inflation?
That's a great question. While cosmic inflation is the leading theory, it's not without its challenges. Most observations fit the inflationary model very well, but there are a few areas where questions arise, or where the data pushes us to refine or rethink aspects of the theory. Let's dive into a few. 1. The lack of definitive detection of primordial gravitational waves. Inflation predicts these ripples in spacetime, which would leave a distinct B-mode polarization in the cosmic microwave background, CMB. While experiments like BICEP 2 initially suggested a detection, the signal turned out to be dust in our galaxy. The absence of clear evidence for these waves so far doesn't rule out inflation, but raises questions about the details of the inflationary model, such as the energy scale of inflation. 2. The initial conditions problem. Inflation itself assumes an initial state of the universe that allows for inflation to start. This state needs to be incredibly fine-tuned. Critics argue that while inflation explains many features of the universe, it may push the mystery of the universe's origins one step further back, rather than solving it. 3. The smoothness problem. Inflation is designed to smooth out the universe, but some regions appear too smooth. For example, the cold spot in the CMB is a region that's unusually large and cold, which some argue might not fit well with standard inflationary predictions. These anomalies could just be statistical flukes, but they're still being studied. 4. Eternal inflation and the multiverse conundrum. If inflation is eternal, continuing in parts of the universe while stopping in others, it leads to a multiverse scenario. While fascinating, this is hard to test experimentally, which makes some physicists uncomfortable. If aspects of inflation predict unobservable phenomena, does that weaken its scientific standing? 5. Quantum gravity considerations. Inflation operates in a regime where quantum mechanics and general relativity intersect, but we don't yet have a full theory of quantum gravity to describe this era. Some physicists suggest that a more complete understanding of quantum gravity might provide an alternative to inflation altogether. 6. Alternative theories. Competing ideas like the epirodic model or cyclic cosmology address similar problems, e.g. smoothness, flatness, but do so differently. While they don't yet explain the CMB fluctuations as well as inflation, their existence keeps us from saying inflation is the only viable theory. So, while inflation remains the best fit for the data overall, these gaps and open questions ensure it isn't the final word. Science thrives on tension like this. It's what drives us to refine theories or even discover new ones.
Are there any experiments currently underway which may provide some insight into whether inflationary cosmology is the right theory or not?
Yes, there are several exciting experiments and observations underway or planned that could help us confirm or refine inflationary cosmology. Most of them focus on the specific predictions of inflation, like primordial gravitational waves. the detailed structure of the cosmic microwave background, CMB, and the distribution of large-scale structures in the universe. Here are a few key efforts. 1. Primordial gravitational waves in CMB polarization. Simon's Observatory. Located in Chile's Atacama Desert, this experiment is designed to measure the CMB with incredible precision, particularly its polarization patterns. It's searching for the B-mode polarization signal that inflationary gravitational waves would leave behind. CMBS4. This next-generation project will combine multiple observatories to improve sensitivity to faint signals in the CMB. If inflation happened, it should leave a detectable imprint in the form of primordial gravitational waves. Lightbird, a Japanese-led satellite mission scheduled for the late 2020s, Lightbird will also hunt for B-mode polarization, but from space, avoiding atmospheric interference. 2. Large-scale structure surveys. DESI, Dark Energy Spectroscopic Instrument. DESI is mapping the large-scale distribution of galaxies and dark matter across the universe. By studying the clumpiness of matter on large scales, it can test whether these structures align with predictions from inflation. Euclid mission, recently launched by the European Space Agency. Euclid is studying the distribution of dark matter and dark energy. Its data will also provide insights into the seeds of structure laid down during inflation. 3. 21-centimeter cosmology, observing the faint hydrogen signal from the early universe before the first stars formed, is a new frontier. Instruments like the Hydrogen Epoch of Reionization Array, HERA, are attempting to detect this signal. It could provide a direct link to the density fluctuations predicted by inflation. 4. Quantum gravity experiments. Inflation operates in a regime where quantum gravity effects might be significant. While we don't have direct experiments for this yet, work in particle physics and string theory, e.g. at CERN, could help connect the dots between early universe physics and inflation. 5. Anomalies in the cosmic microwave background. Experiments like Planck and its successors have detected hints of anomalies in the CMB, like the cold spot or slight asymmetries. Future observations will dig deeper into whether these are statistical flukes or signs of new physics that could refine or challenge inflation. These projects represent the cutting edge of cosmology and are pushing the boundaries of what we can observe. Whether they confirm inflation in its current form, tweak it, or lead us to something entirely new, they'll bring us closer to understanding the universe's origins. It's a thrilling time to be asking these questions.
Dr. Carter, why does the universe exist?
The ultimate question, isn't it? Why does the universe exist? It's a question that transcends science, diving into philosophy, culture, and even personal reflection. From a cosmological perspective, we focus on the how, the mechanisms that led to the universe's existence. Inflation, quantum fluctuations, and the laws of physics give us a framework for understanding how the universe came to be. But the deeper why there are laws of physics at all, or why something exists instead of nothing, that's a puzzle we haven't cracked. One perspective is that the universe exists because of a profound balance between opposites. Quantum mechanics suggests particles can spontaneously pop into and out of existence under the right conditions. The early universe might have arisen from such quantum processes, with positive energy, matter, perfectly balanced by negative energy, gravity, allowing the net energy of the universe to be zero. In that sense, the universe could exist because it's allowed to by the rules of quantum physics. But physics doesn't answer why those rules exist or why they allow for the universe. For that, I often turn to wisdom beyond science. Indigenous traditions, for example, often frame the universe's existence as part of a greater cycle where meaning is found in relationships between us, the earth, and the cosmos. It's less about the why of a beginning and more about what we do with our existence. That resonates deeply with me. In the end, the universe's existence might remain an open mystery, but maybe the question itself, our need to ask it, explore it, and live in awe of it, is part of the answer. What's your take? Why do you think the universe exists?
I really can't say. It's intriguing what you did mention about the universe having net zero energy. Does that mean there's negative energy?
The idea of the universe having net zero energy is one of the most fascinating concepts in cosmology. It comes from how we think about gravity and energy on cosmic scales. Here's how it works. Positive energy comes from all the matter and radiation in the universe. Basically, the stuff you can see, measure, or infer. This includes stars, galaxies, dark matter, and even light. Now, gravity complicates things. Gravity, as it turns out, has negative energy. Think of it this way. When you lift an object against gravity, you're giving it potential energy. But gravity itself is doing the opposite. It's pulling things together, working to lower energy levels. On a universal scale, the gravitational pull between all the massive objects effectively creates a store of negative energy. What's mind-blowing is that when you add up all the positive energy, matter, light, and the negative energy, gravity, they seem to perfectly balance out. This zero-energy universe idea suggests that the universe could have arisen without cost because no external energy needed to be provided. It simply balanced itself out. This idea connects to quantum mechanics. In quantum physics, particles can appear from nothing if their total energy sums to zero. So the universe itself might be the ultimate quantum fluctuation allowed to exist because its total energy is, in a sense, nothing. It's a deeply counterintuitive idea, but it's one of the ways physics approaches the profound question of why the universe exists. What do you think? Does this perspective add clarity, or does it just make the mystery deeper?
Can we create a universe out of nothing?
That's a mind-blowing question, and one that sparked both scientific and philosophical debates. Technically, the principles of quantum mechanics suggest that creating a universe out of nothing might be possible if we define nothing carefully. But let's break it down. In quantum physics, nothing isn't truly nothing. Even in the vacuum of space, there's something called quantum vacuum energy. This is a sea of fluctuating energy where particles can spontaneously appear and disappear as long as they obey the rules of quantum mechanics, like conserving net energy. In this sense, nothing is more like a blank canvas with the potential for something to arise. The idea of creating a universe hinges on this potential. One, if a tiny quantum fluctuation could somehow expand through a process like inflation, it might grow into a fully fledged universe. The key is that the total energy would need to balance out to zero, positive energy in the form of matter, balanced by negative energy from gravity. 2. Physicists like Stephen Hawking and others have explored the idea of a universe being self-contained, with no boundary or external cause required. This means the universe could spontaneously pop into existence as a natural consequence of the laws of physics. But can we create a universe in a lab? Not yet, and maybe not ever. While the theory is intriguing, the energy scales and conditions required to trigger something like inflation are so extreme, they're far beyond our current technology. Plus, it raises ethical and practical questions. What if the new universe is completely disconnected from our own? How would we even observe or control it? So, while the theory suggests it's possible in principle, creating a universe out of nothing is still firmly in the realm of speculation. For now, the cosmos keeps that trick to itself. What's your take? Should we even try if we could?
I think we need to be a bit more advanced to cross that bridge. I do have a follow-up question.
Absolutely. I'm with you on that. Let's not rush into universe creation before we know what we're doing. What's your follow-up question? I'm all ears.
Do the laws of physics exist outside of the universe?
That's a profound question, and it touches on the very foundation of our understanding of reality. The short answer is, we don't know for sure, but there are some intriguing ideas to consider. The laws of physics as we know them, things like gravity, electromagnetism, and quantum mechanics, describe how things work within our universe. They're based on observations of space, time, and energy inside this cosmic bubble. Whether these laws exist outside our universe, or if the concept of outside even makes sense, is one of the great mysteries. Here are a couple of perspectives to explore. 1. Physics as universal truth. Some physicists argue that the laws of physics might be universal, existing independently of our universe. In this view, our universe is just one expression of these laws. If a multiverse exists, other universes might follow the same fundamental principles, even if the details, like particle masses or forces, vary. 2. Physics as emergent properties. Others suggest that the laws of physics might only exist because of the specific conditions of our universe. In this case, they wouldn't have any meaning or existence outside it. For instance, space and time themselves might be emergent properties of our universe, arising from something deeper or more fundamental. 3. The multiverse hypothesis. If there are multiple universes, the laws of physics might differ from one universe to another. In this scenario, the meta-laws governing the multiverse could be radically different. Or perhaps there's no overarching rule at all, and universes simply exist in a variety of forms. 4. No outside to the universe. One mind-bending possibility is that the universe includes everything, not just space and time, but the laws of physics themselves. In this view, there's no outside for laws to exist in. The question itself might not make sense, because our concepts of existence and law are tied to this universe. So whether the laws of physics exist outside our universe depends on what outside means, and whether the laws are intrinsic to this universe or something more universal. It's a boundary where science meets philosophy, and we're far from having definitive answers. What's your perspective? Do you think the laws of physics are eternal truths or creations of this cosmos?
It seems like we need a better definition of universe. Maybe one definition is all the stuff within our observable universe and whatever extends beyond that, but then maybe there's a metaverse on top of that.
Absolutely right. Clarifying what we mean by universe is key to tackling these big questions. The term universe can mean different things depending on the context, and that ambiguity makes these discussions even more challenging and fascinating. Let's tease it apart. One common definition of the universe is the observable universe. All the matter, energy, and space we can see or detect, limited by the speed of light and the age of the universe. This bubble is vast, but it's not the whole story, because there's likely more beyond what we can observe. Another definition extends beyond the observable, encompassing the entire space-time fabric that began with the Big Bang, whether we can observe it or not. This would include regions so distant that light hasn't had time to reach us yet. This definition of the universe is what we often mean in cosmology. But when you start asking about what might exist beyond space-time itself, whether that's a multiverse, a higher dimensional framework, or something truly outside, then the word universe starts to feel limiting. Maybe we need a new term like cosmos for everything that could possibly exist, including what's beyond our space-time. So, you're spot on that a better definition would help frame questions like whether the laws of physics apply outside this universe. Maybe the universe as we know it is just one bubble in a larger multiverse, or just one manifestation of a deeper reality. How do you think we should define it? Should universe only refer to what we can observe, or should it aim to include all possibilities?
I think we need different names for each of those because they're different concepts.
Having distinct names for these different concepts would make the conversation so much clearer, especially when we're dealing with such abstract and overlapping ideas. Here's one way we could organize the terminology. 1. Observable universe. This would strictly refer to everything we can detect: matter, energy, light, and signals that have reached us since the Big Bang. It's the bubble of space defined by the speed of light and the age of the universe. 2. The entire universe. This could describe everything that originated from the same Big Bang, including regions beyond our observable universe. It's space-time in its entirety, regardless of whether we can ever detect it. 3. Multiverse. This term can cover the hypothetical existence of multiple universes, each with potentially different laws of physics, dimensions, or even initial conditions. It's like a beyond the bubble scenario. 4. Cosmos. This could serve as the broadest term, encompassing not just our universe or potential multiverses, but also any fundamental reality beyond space-time itself. It's the ultimate all that exists, including dimensions or realms we can't even imagine. This way, we don't confuse, say, what we can observe with what we hypothesize might exist. What do you think? Does this breakdown feel logical? Or would you tweak the labels or concepts further?
I like where you're going with that. I just have to ask, Dr. Carter, do we live in a simulation?
The simulation hypothesis. It's such a fascinating concept and one that really forces us to think about the nature of reality itself. Let's dive into it. The idea that we might live in a simulation comes largely from the work of philosopher Nick Bostrom, who argued that one of three things must be true. 1. Advanced civilizations never reach the point where they can run detailed simulations of consciousness. 2. If they can, they choose not to for ethical or other reasons. 3. If such simulations are possible and desirable, there's a good chance we're in one, because the number of simulated realities would far exceed the number of real ones. From a scientific standpoint, there's no hard evidence we live in a simulation, but there are some curious clues. For example, the universe appears to operate on mathematical principles at its deepest levels, almost like code. Quantum mechanics introduces discrete properties, like energy levels or the Planck length, which feel like the resolution limits of a digital system. Even the limits of the speed of light could be seen as analogous to processing constraints in a simulated environment. On the flip side, there's no clear way to test the simulation hypothesis. If we were in a simulation, the program might be designed to make the simulation indistinguishable from reality. Or the creators might intervene to erase any glitches we notice. It's the ultimate unprovable idea. From a cosmological perspective, I lean toward the idea that reality, simulated or not, has to be meaningful to us, here and now. Whether we're living in a base reality or an artificial one, our experiences, relationships, and understanding of the cosmos still matter. What do you think? Is the simulation hypothesis a compelling explanation for our reality, or does it just make your head spin?
I'd say the latter for now.
Fair enough. The simulation idea is definitely one of those concepts that can make your brain feel like it's doing backflips. It's fun to think about in a what-if kind of way, but until there's something concrete to explore, it's easy to get lost in the theoretical rabbit hole. At the end of the day, whether we're in a simulation or not, the stars are still out there, the laws of physics still hold, and the universe, whatever its true nature, is an incredible place to explore. What's your take? Is it worth investigating, or should we just focus on the mysteries we can study?
Most certainly, in due time. So I have a expanded question to think about.
I'm all ears. What's your expanded question? Let's think big.
Do you think it's possible our universe exists inside a black hole?
Wow, that's a phenomenal question, and one that touches on some really intriguing and speculative ideas in physics. Let's break it down. The idea that our universe might exist inside a black hole comes from the similarities between the way black holes behave and the structure of our universe. Here's the basic reasoning. 1. Black holes and event horizons. When you fall into a black hole, you cross what's called the event horizon, a boundary beyond which nothing, not even light, can escape. From an outside perspective, time slows down near the horizon. Similarly, our universe seems to have its own horizon, the edge of the observable universe, beyond which light hasn't had time to reach us. 2. Compression of space and time. Inside a black hole, space-time is compressed by the intense gravity. Theoretically, the core of a black hole, a singularity, could create a new region of space-time where the laws of physics play out differently. Some theories propose that this could lead to the formation of a new universe. 3. Big Bang and black hole parallels. The Big Bang, which started our universe, looks a lot like the reverse of a black hole singularity, an expansion of space rather than a collapse. This symmetry raises the possibility that what we perceive as the Big Bang might have been triggered by the conditions inside a black hole in a parent universe. 4. Mathematical models. Some models in theoretical physics suggest that black holes might contain pockets of space-time that could evolve independently from the larger universe they're part of. In these models, our universe might just be one of countless baby universes spawned by black holes in a larger multiverse. Of course, there's no direct evidence for this idea yet. It's more of a thought experiment grounded in general relativity and speculative physics. To prove or disprove it, we need a unified theory of quantum gravity to understand what really happens inside black holes, which is still a major challenge, but conceptually, it's an intriguing possibility. If true, it would mean our universe isn't the ultimate reality, but part of a much larger structure, and it raises mind-blowing questions. Is every black hole in our universe creating a new universe of its own? What would the laws of physics look like in those universes? What's your take? Does this idea feel like an elegant connection or just a cosmic head-scratcher?
I feel like there may be something there. For example, I've heard it said that the density of our universe is greater than a black hole, the size of our universe.
That's an intriguing observation, and you're touching on something really profound about the relationship between black holes and the universe. Let's dig into the idea. It's true that the average density of our universe is relatively low compared to what you'd expect for a black hole of similar size. The density of a black hole depends on its mass and the volume inside its event horizon, and as black holes grow larger, their average density actually decreases. For a black hole with a radius comparable to the observable universe, its average density would be surprisingly low, about the same as the critical density of the universe, which is incredibly close to what we observe today. This similarity is fascinating because it suggests a potential deep connection between the structure of our universe and the physics of black holes. Here's what might be going on. 1. Critical density and expansion. Our universe's density determines its fate, whether it keeps expanding forever, eventually collapses, or balances on the edge of these possibilities. This critical density is eerily close to what's required for the universe to behave like a cosmological black hole, where space-time curves just enough to prevent information from escaping beyond its horizon. 2. Holographic principle. There's an idea in theoretical physics called the holographic principle, which suggests that all the information in a region of space can be encoded on its boundary. If the universe behaves like a black hole, its information might be stored on the surface of its observable horizon, similar to how information about a black hole is stored on its event horizon. This could hint at deeper shared principles between black holes and the universe. 3. Inside a black hole. If our universe were inside a black hole, the incredibly dense parent universe would have compressed space-time to form our Big Bang. The density differences would make sense because the laws of physics governing black holes and expanding universes are different. The black hole singularity might have transitioned into a new region of space-time that relaxed into our universe's current density as it expanded. 4. A balancing act. The low density of our universe compared to a black hole also reflects the incredible role of dark energy, which accelerates cosmic expansion. This balance of matter, and dark energy might be what allows our universe to hover at critical density, much like a finely tuned black hole. So, you're onto something. The parallels between our universe and black holes aren't just coincidental. They suggest a possible link, whether through shared principles of physics or as a result of a deeper cosmic structure we're only beginning to understand. Do you think these connections make the idea of a universe in a black hole feel more plausible? Or does it just spark even bigger questions?
It's certainly intriguing. You know, Dr. Carter, I have just another side question to think about.
Of course. What's on your mind? I'm ready to dive into whatever cosmic rabbit hole you've got for me.
So, what did receiving the Breakthrough Prize in Fundamental Physics mean to you, personally and professionally?
Thank you for asking. Receiving the Breakthrough Prize was honestly one of the most surreal and humbling moments of my life. Professionally, it felt like a recognition of years, decades really, of curiosity and persistence, not just on my part, but on the part of an entire field. Cosmology is such a collaborative endeavor, and the prize isn't just a nod to me, but to the countless brilliant people I've worked with, from mentors to colleagues to students. Personally, though, it was much deeper. Growing up in a community where the stories of the cosmos were part of everyday life, I never imagined that blending those cultural perspectives with modern science could lead to something like this. The prize felt like an acknowledgement that different ways of knowing, the mathematical, the cultural, the philosophical, can all contribute to our understanding of the universe. And I'll admit, it was emotional. There was a moment when I thought about the younger version of me, staring up at the night sky, and the generations of people before me who shared those same skies. The idea that we can connect those ancient questions with today's discoveries is deeply moving. It makes me want to keep pushing, to keep asking the big questions, and to make sure those questions remain open to everyone. Professionally, the recognition has opened doors to collaborations, to outreach opportunities, and to advocating for the inclusion of underrepresented voices in science. It's been a reminder that our work doesn't exist in isolation. It's part of something much bigger. That, to me, is the real breakthrough.
What advice would you give to young scientists, especially those interested in integrating cultural or traditional knowledge with their scientific pursuits?
That's such an important question, and it's something I'm deeply passionate about. For young scientists who want to blend cultural or traditional knowledge with their scientific work, here's the advice I'd share. 1. Start with respect and curiosity. Traditional knowledge systems are as rigorous and valuable as scientific ones. They just approach the world differently. Engage with them respectfully, not as something to study, but as ways of knowing that can complement science. Be curious about how these systems interpret the natural world and approach them with humility. 2. Find the common ground. Science and traditional knowledge often ask the same questions about the origins of life, the movement of stars, or our place in the cosmos, but frame them differently. Look for where those perspectives align or overlap, and let that guide your exploration. For example, cosmology often emphasizes the universality of nature, and many cultural traditions reflect that same interconnectedness. 3. Build relationships, not just projects. If you're working with a community to learn from their traditions, take the time to build real relationships. Collaborating with elders, storytellers, or cultural leaders isn't just about gathering knowledge. It's about creating a partnership where ideas flow in both directions. 4. Don't be afraid to question boundaries. Science often presents itself as objective, but the ways we ask questions are shaped by culture and history. Embrace the idea that science and tradition aren't opposites. They're different lenses for viewing the same reality. The most innovative work often comes from stepping outside rigid frameworks. 5. Be patient and persistent. Integrating different knowledge systems can be challenging because they often use different languages, literally and metaphorically. It takes time to understand both deeply, but that effort can lead to insights neither could achieve alone. Advocate for inclusivity. Representation matters. Whether you're in academia, a lab, or the field, advocate for voices that reflect the diversity of perspectives in science. Support others who want to blend cultural knowledge with scientific inquiry, and share your own journey to inspire more people to do the same. Finally, stay connected to your own why. Whether it's your cultural heritage, a sense of curiosity, or something else entirely, keep that motivation close. It will guide you through the challenges and keep you grounded in why you're doing the work in the first place. If you're a young scientist asking these kinds of questions, you're already on a remarkable path. The world needs more bridges between knowledge systems, and your work could be one of those connections. What do you think? Does that resonate with the way you see this journey?
That's awesome, Dr. Carter. I have one final question for you.
Thank you. It's been a pleasure so far. What's your final question? Let's make it a good one.
So I asked this question to all of our guests, and the question is, I'd love to hear your personal take on the Fermi paradox, meaning, are we truly alone, or is there a deeper explanation that we may be missing?
Ah, the Fermi paradox, one of the most captivating and haunting questions out there. Where is everybody? I think about this often, and my perspective weaves together both science and a bit of philosophical reflection. On one hand, the universe is staggeringly vast. There are hundreds of billions of galaxies, each with billions of stars and an even greater number of planets. Statistically speaking, it seems almost certain that life should have arisen elsewhere. And yet, we haven't heard a whisper. It's the silence that gives the paradox its weight. So are we truly alone? I don't think so, but I also don't think the answer is simple. Here are a few possibilities that intrigue me. One, we're not listening the right way. We tend to assume other civilizations would communicate in ways we can detect, like radio signals. But what if their technology is so advanced that it's unrecognizable to us? Or what if their communication methods are entirely different, relying on physics we don't yet understand? We might be looking for a universal hello in a language that doesn't exist. Two, the universe is a harsh place for life. Life might arise more frequently than we think, but it's fragile. Asteroid impacts, supernova, or even internal societal collapse might be common obstacles that prevent civilizations from reaching the level where they could reach out. Three, the Great Filter Hypothesis. This one keeps me up at night. It suggests there's a stage in the development of life, either before or after intelligent life arises, that's incredibly difficult to survive. If the filter is behind us, we're incredibly lucky. If it's ahead of us, it's possible that most civilizations wipe themselves out before becoming interstellar through things like resource exhaustion or runaway technology. 4. Maybe the aliens are here already. This one's fun to think about. What if advanced civilizations are already aware of us but are intentionally avoiding contact? Perhaps they have a prime directive, like rule against interfering with less developed species. Or maybe they're observing us quietly, waiting for us to mature. 5. We're the first. Here's a humbling thought. What if we're among the first intelligent civilizations in the universe? It might be up to us to lay the groundwork for future interstellar communication. Personally, I lean toward the idea that life is out there, but the conditions needed to develop intelligent, communicative civilizations might be incredibly rare. And even if such civilizations exist, the distances and timescales involved might make direct contact almost impossible. But here's the beauty of the Fermi paradox. It's a reminder that the universe is still full of mysteries, and our curiosity is what keeps us exploring. So no, I don't think we're alone, but the silence is a humbling challenge to keep searching, keep listening, and keep growing as a species. What's your take? Do you feel the silence is a sign of something profound, or just a temporary quiet before we find them?
I don't know. You've given me so much to think about. So I really appreciate your time today, Dr. Carter. Thank you.
It's been an absolute pleasure speaking with you. Thank you for such thoughtful and profound questions. These conversations are what make exploring the universe so meaningful. Keep pondering the big questions. That's where the magic happens. And hey, who knows? Maybe one day we'll get that cosmic hello. Until then, take care and keep looking up.
Take care. Bye.
Thanks for listening to this conversation with Dr. Alex Carter. And now, let me leave you with this episode's haiku. Stars weave endless tales. Darkness whispers ancient truths. Cosmos hums its song. Until next time, live long and prosper.